Hi, this is Phil Ferrier. Before showing you the execution of the jobs for task 1, I thought I would give you a quick overview of the architecture and what we have set up at Amazon so that you get a better understanding of what it is I'm going to show you next. So we basically set up a EMR cluster at Amazon with a master node and several core nodes. The stack we use on the master is RStudio server on top of R, and we've installed several packages to allow us to talk to Hadoop. RHDFS, which is just an abstraction of HDFS, RMR2, which allows us to write MapReduce functions, and a very nice package called Plier MR. If you know anything about R, there's a package called Plier, which is a very powerful data manipulation package. And it's basically Plier, the same functions pretty much, but running MapReduce. On the nodes, we have the same packages pretty much. R and those packages. We don't have to server because we don't really need to interface with the core nodes. And on the master, we also have RJDBC, which is an R package to that's on top of the Java database connectivity interface, so we can talk to basically any database. And I'll actually show you the request we run against the DynamoDB, but on a RStudio app client, at home. For this Capstone, the data was extracted from compressed CSV files contained on an EBS drive, out of which we created two datasets, one that contained information about all years, and another one about the year 2008. The first one was used to answer the first 6 data mining questions, and the year 2008 CSV was used to answer the last data mining question. Out of the CSV columns, we only kept the ones that were relevant to the data mining question. We discarded incomplete observations based on that set of columns, and for performance reasons, we created composite keys and collapsed date information. Finally, the data was loaded to HDFS using the RHDFS package. To find the top 10 most popular airports, we grouped the data by origin airport and counted the flights. We grouped the data by destination airport and counted the flights. We then joined the two sets of results by airport, summed the incoming and outgoing flights, ordered the results, picked the top 10. To find the top 10 airlines by on-time arrival performance, we grouped the data by carrier, measured the average arrival delay in minutes, ordered the results, picked the top 10. To rank each day of the week in terms of on-time arrival performance, we grouped the data by day of the week, measured the average arrival delay in minutes, ordered the results. To find for each airport what were the top 10 carriers in decreasing order of on-time departure performance, we grouped the data by origin airport, then carrier, measured the average of departure delay minutes within each group, ordered the results by decreasing average within each group, kept the top 10. To find for each airport X what were the top 10 of airports Y1 to Y10 that had the best on-time departure performance from X, we grouped the data by origin airport, then destination airport. Within each group, we measured the average of departure delay in minutes, ordered the results, kept the top 10. To find for each pair of airport XY what were the top 10 carriers in decreasing order of on-time arrival performance at Y from X, we grouped the data by composite key origin destination, then by carrier. Within each group, we measured the average of arrival delay in minutes, ordered the results, kept the top 10. To find for each pair of airports XY what was the mean arrival delay in minutes for a flight from X to Y, we grouped the data by a composite key origin destination and measured the average of arrival delay in minutes for each group. To establish if the popularity distribution of airports followed a ZIP distribution, we ran the same MapReduce code as in question 1.1 to collect results for the entire list of airports, not just the top 10. We then plotted rank and number of flights on a log-log scale. If the data had followed the ZIP distribution, this would have resulted in a straight line. It did not. The data, however, can be equally well described by a log-normal distribution or a Weibull distribution. By plotting the CDFs of actual and theoretical distributions, as well as the probability plots, we can tell that both log normal and Weibull are good fits in the denser part of the data distribution. By looking at the QQ plot, we can tell the log normal fit isn't as good as the Weibull fit at the tail of the data distribution. For details about the somewhat more complicated implementation necessary to answer question 3.2, please refer to the written report. Time to run the queries. This is our studio. We're at home on the West Coast, and the cluster was set up on the East Coast, and our service provider is Comcast, so not really too much in the delays connecting to the database. Again, so this is running R, and we're going to use a package called RJDBC, which allows us to talk to the database DynamoDB that we have set up at Amazon. This is just a bunch of magic to do that. We basically have to say, we're using DynamoDB on the East Coast, and here are our keys to connect to our database. And this is our list of tables. We have a table per question. If you haven't used DynamoDB, it looks like this. The tables are here, and we have our partition key here, and the results, which are, for most questions, a list of neighborhood pairs. If you care about the details of the schemas we used, please go back to the report where this is detailed for each question. And at the end of the report, we've also put together, all the results. So you can, if you validate the results here, or if you'd like, you can pause the video and validate them over there. So let's run the queries. Question 2.1. And we get our results nicely ordered. Again, we're just putting together very simple SQL statements where we're asking for the results for whatever input we were providing by the Coursera staff to give an answer to. So we've done group 1, question 1. We're going to do 2.2. You can look at the results also for 2.3. And you notice that we use composite keys basically. And you can go back to the report to see what we do. But it's really a matter of trying to see get the best performance from the database. Question 2.4. And again, we get our results in terms of average arrival delays. And question 3.2 is where we also have composite keys where we want to provide what is the best trip to go from, let's say, CMI to LAX with a layover in Orlando on that day. And this is what we get. And the flights we chose were always the for this example here, so they would have to be 2 days apart. So this is leaving on the 10th day of June, and the layover date is 12th, and we always return the flight in the afternoon that had the best performance in terms of arrival time. And we have also here the morning flight on the first day, and it's also the flight with the best performance in terms of arrival time. That's it.